Okay, so first of all, thanks for the organizers. And of course, you're under pressure that in 2 years we want to hike up to 3,000 meters.
Not with me. You can.
Okay, so now what I want to talk about is joint work with Martin Christensen and Jan. Martin is here, of course, everybody knows so, and this is part, what I talk about is also part of Martin's PhD. So all complaints go to him. Since the artwork was done by him, so therefore. Okay, so the model is pretty basic. So what the model is, you can think of maybe as an application, you can think of a metal. Just I use this here. And a piece of metal, and usually for a metal you can think of that you have ions which are placed on crystal-like, and then you have electrons running around. So, but a little bit simplified model, which was introduced actually by Wigner in the 30s, is that you think of that the ions are uniformly distributed in the background, and then you have electrons here moving around. So, there's unfortunately no other color. So the interaction among the electrons is just Coulomb. So you see, I use here just for physicists, I use here units where h bar is 1, mass of the mass is 1, and the electric charge is 1. So therefore, I don't have that here. So now the model here is simply the kinetic energy of the electrons, and then the interaction among the electrons, and then you subtract the energy of the background. So now you might wonder why there is no interaction of electrons with the background here. So now you have to think of this as maybe being on a torus. So the charge is uniformly distributed, therefore the charge does not really feel any force because it's uniform. And the effect of the background is basically given just by subtracting this part. Then of course the electrons are fermions. Now we're thinking here of a high density limit. So the limit will be density to infinity. So the density is the number of particles divided by the volume. So from a physical point of view, you can think volume going to infinity. When I'm talking later about a mathematical theorem, we will fix basically the volume of size 1. But for the moment, you can think of what we know from physics literature. So basically, we look at the Hamiltonian, and one of the rigorous statements going back to the 70s of Lieb and Nanhofer, somehow short after Lieb and Leibowitz proved the existence of the thermodynamic limits for basically for matter, for molecules and for atoms and molecules. Lieb and Nanhofer proved that this model, there exists a thermodynamic limit, meaning that if you look at the infimum of the spectrum, divide by the volume, and then you basically fix the density rho and go with n or the volume to infinity, then this has a definite limit which only depends on the density rho. So now the question is, what can you quantitatively say about the energy of this model, which is called Jellium, depending on rho, in the limit of large density. So, here's the next slide. So of course, and it was when you go back to the beginning of quantum mechanics, and in short, after the beginning of quantum mechanics, the people realized that one way to look at the leading order is to consider the Hartree-Fock energy, meaning that you that you ask what is the energy if you minimize over size, which are n-body slated determinants, and one of the so first of all, this is basically pretty easy to calculate how this depends for large rho. So, and one mathematical statement, and maybe the only rigorous mathematical statement about the energy behavior for large rho of this Cellier model, goes back to Graf and Soloway for around almost now 30 years ago, based on a correlation inequality by Volker Bach, where they state that the energy of the cellium is to leading order given by the Hartree-Fock energy plus lower order. So now, so if you open a physics book and you look at this, I mean, there are many books who considers actually the ground state energy of this problem. And when they talk about Hartree-Fock, is what they usually do, they plug in the Slater determinant, where they use a product of plane waves, and choosing the plane waves so that the moment of the plane waves is just taken in a way which minimizes just the kinetic energy. So basically, the non-interacting system. So when you look at the physics book, they usually plug in here the n-body state which you get by a Slater determinant of the n-lowest plane waves, and calculate this energy. And what is interesting, in a joint paper with David Gontier and Mathieu Levin, we actually proved, and I think it came to a little bit of a surprise to us, that the Hartree-Fock energy, when you minimize over any Slater determinant, is basically exactly given by the energy of plane waves, plus some corrections which are exponentially small. So I mean, at least I mean, we never thought about that, so it came as a little bit surprise, but that basically justifies what you see in the physics literature, that when you calculate the ground state energy in the Hartree-Fock approximation, to only use plane waves. So now one of the main questions is, how do you go beyond that? And that was a discussion in the physics literature which goes back to the end of the 40s and beginning of the 50s, or even started a little bit earlier. Maybe now let me say what is known if you want to go beyond Hartree-Fock. So first of all, a few things. So the people realized pretty soon that the Hartree-Fock is insufficient to describe important quantities, for example for metals, namely a specific heat or what is called cohesive energy. So they knew already that you have to go beyond that. I'm here referring to a paper of Badin from the 30s. And what Wigner did, he basically came up with a phenomenological model to describe that. And so I also cited here Heisenberg, because there was an interesting paper with the title "The Theory of Superconductivity," where he argued that you cannot go beyond Hartree-Fock by just using second-order perturbation theory, because what you get infinities. And he interpreted this kind of infinities as having something to do with superconductivity. I think Pauli told him that he can sell the theory on the flea market. No, I think that was really what he said. So then they first really attempt to go here beyond the Hartree-Fock energy was by a series of papers of Bohm and Hainzl. There were 4 papers. The first 2 of them were about the classical theory, and then there were 2 about the quantum part. The last one was by Hainzl alone, and they coined something. They had some approximation which they called random phase approximation. So now, yeah, I mean, what I will tell you now, there will be no random phases, because later one really saw how you can describe that without using random phases. But the interesting thing is, I saw on YouTube once a talk by Hainzl. I think Hainzl died, I don't know, 2 or 3 years ago. And in his later ages, he gave a talk you can find on YouTube where he really described exactly how they found, how they basically treated this gallium system. And he said he regretted it heavily to call it random phase approximation, because if he would not have done it, everybody would have called it Bohm and Hainzl approximation. So what basically you can describe what they did as taking the Hamiltonian and decomposing it into 2 parts. One which describes a collective motion of electrons for some small momenta, and they called that plasmons. And plus individual electrons, which basically travel in the background of the plasmons and therefore get the screened Coulomb. So they calculated then the energy by saying, okay, we can calculate the collective plasmons, and if you have a screened Coulomb, then you can do second order perturbation theory. This is basically how they got beyond the Hartree-Fock energy. And what they got, at least what they stated, and what you also read in Pine's book, that this fitted much better the experiments than what was known before. So then, as a next step, so Gell-Mann and Bruckner basically came up with a formula. So they went beyond. So the next term depends. So you see that the Hartree-Fock energy, the kinetic energy goes like density to the 5/3. The exchange energy is rho to the 5/3. And then the next one goes like proportional rho log rho, and the next one is just rho. This is now I know why one can do this mistake. So okay, so this was the wrong one. And of course, they really came up with the precise coefficients C1 and C2. So what Gell-Mann and Bruckner did, they wrote down Feynman diagrams, and then they were basically resumming a partial set of Feynman diagrams. And I just want to give you a picture for that. So here I just took from a book. I don't remember exactly which one. So this is just perturbation theory. So when you think of so if the Hamiltonian, let's say Hn, is given by the kinetic energy plus the interaction, then what is written here as W0, that is just the expectation value of the free Fermi state with the potential. So this is first order perturbation theory. And then of course, this is the first part. And then of course, the next part is just by second order perturbation theory. So this is what is denoted here as W0. This is just the total kinetic energy of the field Fermi ball. So this is what we denoted as W0. So in second order perturbation theory is then doing 1 over T minus W0. This is second order perturbation theory. this is what you find here, and then of course you go on like that. 1 over t minus 0b . So, and maybe I will basically come back to that. So when you basically write the interaction in momentum space, then usually what you find, you can write it as you have the scattering of two particles, one with momentum p and one with momentum q. Then then you feel basically the interaction here in Fourier space, and here you have maybe p plus k and q minus k, so that you have a momentum conservation. And just as a remark, the first two, so now you see, you plug it in here, and basically what you do, you do a trace. So trace means you basically connect the arrows. So one way is to connect it here. This is, when you do that, then p plus k has to be equal to p, so k has to be 0. And this is the first one here. And that is actually the direct interaction, which is by definition excluded by the model. So you just subtract that. And when you then combine it the different way, then you get here, this is the exchange term. So now you could write that down, and so on. So I will come back to this picture later. But what is the important thing? What I wanted to tell you, what Gell-Mann and Bruckner did. So you could go on like that, and you get extremely many different diagrams. But Gell-Mann and Bruckner said, okay, when we go beyond Hartree-Fock, the only thing we need is basically the Hartree-Fock term. Well, this is cancelled by the background, plus a specific group of diagrams which has a specific nature, namely which is like, you can consider that as a kind of bubble where you interpret one as a particle and one as a whole. So you have a particle hole bubble interacting with other particle holes. So you have basically interaction only of bubbles. What that means, we come back to that later. But what they did was just they were summing up those specific class of diagrams. And what was the interesting part of that? That each of those diagrams was divergent. So basically, they were saying that you have all these divergent diagrams, but if you sum them up, they get finite. They become finite. And then there was one more diagram which they had to include because this was proportional to rho, and so they came up with this formula. So I also want to show this picture because afterwards we give a theorem, and you see that the theorem is non-trivial because it's not perturbative. I mean, you really have to sum up a full class of infinite diagrams in some sense. But also let's go back to that. So what I said, then Gell-Mann and Bruckner come up with a specific way, and shortly after, so and what you see in interaction is the interaction of electron pairs. Basically one hole, which is one inside and one outside. This will be important. So, and I think even in the same paper after the Gell-Mann-Bruckner, in the same volume, Sawada came up with a different approach because he rewrote the Hamiltonian in such a way that he took the interaction, and what he basically retained was only the pair-pair interaction. And I will come back to that later, so I will really go into that. And then treating this Hamiltonian as something quadratic. So this is basically the main idea, which is here called as Bosonization approach. So actually, who called that Bosonization approach? I mean, maybe Niels would know.
Was it Haldane?
before it was in this age. So it goes back to you.
Yeah, it's because of you.
Okay. Yeah, okay. So this was now basically a little bit a review of the history. Yeah, that was the graphic. So we would like to prove, as actually it would be nice to prove it in this full general context, namely looking really at Coulomb in a thermodynamic limit, and that is really hard. So what we and also others, I will come back. Is to look at, to simplify the model a little bit, and with a little bit I mean you fix basically, you don't take the infinite volume limit. So now maybe I try this one. So you take just the maybe I don't need that here for the moment. You take a box of size 1. You take a box of size 1 and basically put n particles in it, and the large density limit. So then the density, okay, you take the box with side length 2 pi, then the density is n over this volume. 2 pi to the 3. I think I can do. So and now how do we fix? So now we fix the number of particles. Now I take a picture. So
Christian, since the talk is recorded, if you write there, so the people don't see anything. So either you move the thing or you write at the blackboard.
Which is this one?
They're the same, but
okay, but here it is nice because you see why I want to use this one. Because you can see the lattice here, and that can describe the momenta. So basically, we take here just the Fermi ball. We take the Fermi ball. Now, if this is maybe the middle, then we say this is kf, so the Fermi momentum. And now, how do we fix n? So n is exactly the number of momenta in C3 which are inside the ball. Yeah, so this is just the number. So actually, as it is written here, so this is the number of points which are inside of this lattice. And of course, now what is the relation? So usually, so the relation. The relation then is, of course, if you would have the continuum, then the relation between kf and rho would be 4 pi over 3 kf cube is rho. Now, of course, you count the points inside, so to leading order, you can say, and in that case, rho is equals to, what was it, n over 2 pi over 3. So n goes like, kf goes like n to the 1/3 if you want. But so for technical reasons, it's basically important that we choose n so that you basically fill the whole thing. Then the Hamiltonian is essentially, this is really not so easy to do this. So the Hamiltonian is a little bit is a little bit different. Namely, we take we scale that by 1 over kf, and the 1 over kf is so that the interaction here is then proportional to the kinetic energy. So it will be simplified by taking the mean field approximation. Now we want to take Coulomb, still want to take Coulomb, but we're on the box. So what we do, we take the Fourier, the 1 over k square, and take the Fourier transform. And we do not take the k equal to 0, and by not taking the k equal to 0, this is equivalent to subtracting the background. Yeah, so this is this minus rho square. Okay, and here it's just denoted here that the corresponding Hartree-Fock energy is exactly again the expectation value of the free Fermi sea. So basically filling all the ball with plane waves, taking the momenta inside the plane waves plus something which is exponentially small. Okay, so this is a little bit a simplified model concern if you compare to what we had before in the full Cellium. So if you take the Gell-Mann-Bruckner result, and now you can of course translate the calculations of Gell-Mann and Bruckner immediately to the model which we had before, and therefore this is kind of denoted as a conjecture because anyway, I mean even in the Gell-Mann-Bruckner formula it's not a proof, so as a mathematician you would call it a conjecture, the physicists might disagree. So now what is the goal, of course, is basically to prove at least this thing. And before commenting here more on what is here, then I will tell you that the next slide will tell you that basically we gave a proof for an upper bound in that case, and a proof for the lower bound hopefully will be reachable in not too distant future. And for regular potentials, there were really equality. I will come back to that later, but just that you might wonder if I consider here this slide, that there was already something proven. So now the conjecture is formulated so that we basically translate what Gell-Mann and Bruckner did. And the translation is basically only saying that you don't take the infinite volume limit, and you just scale the potential by 1 over kf. That then has a little bit, I mean, that of course means that these terms, so first of all, there's written in 2 terms, so the first of them should correspond to what we had graphically before. Go back to this picture, graphically before as this infinite sum. And this was denoted as the correlation, the bosonic correlation energy, and this one term is the exchange correlation energy. Now let's go here again. So the bosonic correlation energy is here described in this part. I will comment on that in a second. And so as you remember before, I told you that the Gell-Mann-Bruckner was like rho log rho. Now we divide, rho was kf to the third. So therefore, by dividing by kf, basically the first one goes to quadratic. So basically you divide by kf squared and you get the behavior here. And that is proportional to kf. So now when you, so maybe just as I think, so I don't have so many slides, so I have time. So
could you please pull it
closer. Do you really think somebody watches that? Okay, so if we look at the first term,
why don't you use a blackboard? No?
yeah, I will use it in a second.
Partly, okay, fine.
Okay, yeah. So just if you just to see what this term is, you see the function f. The function f is log 1 plus x minus x. So the log 1 plus x you can expand in a power series of x. The first is linear, so this cancels basically by minus x. There is no linear term. The next is quadratic. So you basically have the square of that. And when you take the integral, so when you take here basically the integral of, So you sum over, when you take the square, you sum over P and Q, lambda K of P divided by lambda K P square plus T square, and there is a lambda K of Q if we square it. Lambda kq plus t square. If you integrate dt from 0 to infinity and you use your classes on complex analysis, you get 1 over lambda kp plus lambda kq. So you get that, and then from here you get the, basically now let me write it as 1 over k to the 4, because you have a 1 over k and you have a square. Now this was bad. So if you square that, so you sum here over all k and over p and q, which is here described summing over p from what is called Lk. So now what is that? What is that? So what you do here for a given momentum k, so Bf is the Fermi ball, so you take here Fermi ball, let's say this is the middle, you shift it by k, so you get the second ball, and then what you have, you see P has to be outside, no, has to be in the shifted Fermi ball without the Fermi ball. So it's basically all the points here, which are in this part. This is Lk, and L stands for Lun. L stands for Lun here. So these are all these points. And now you might ask. So you have 1 over k to the 4. You might ask. So this is basically, now I can write that as 1 over k to the 4. And the energy here, what is lambda kp? What does that mean? So now you can interpret that actually as the energy, yeah. So now I go here again. So basically, if you take here one point inside of the Fermi ball, let's say this is or I create one outside. Let's do that. I create here one outside. I call that P, and if that is here my P minus K, then if you think of how do you change the energy corresponding to the field Fermi C, you create the particle outside and you make a hole inside. So the change in energy is you add P square and you subtract P minus K square. So this is basically the energy change. This is the energy change of the kinetic energy of the full Fermi C when you make a hole inside and a particle outside. So so you can also write that. Siri and I have a strange relationship. So you can write that as K plus P plus Q, and you can sum over that. Now you might wonder how many. So basically, what is the volume of the Lun? So the volume of the Lun is let's say K times Kf square, or it is the minimum of this, and when you of course shift it outside, then it is the volume of the whole thing, which is Kf to the 3. So you get the K square here. I just want to tell you now. So if you don't look at the unit box and make an infinite volume limit, then from the integration in P and Q, you would get something for small k, you get here a k square, and then you have another basically k here. So you have So you have 1 over k to the 3 all in all, and that is divergent. So this is basically a divergent diagram if you look at the infinite volume limit. For the finite box, it is fine. So for the finite box, actually, you could extend that in an infinite volume, so that in an infinite sum, so that each sum is finite. But for the infinite volume limit, each of the expressions here alone would be infinite. But that part makes sense even in the infinite volume limit, and that's why also we like to formulate it this way. Okay, so and this is the exchange term. So this is this one contribution I told you. Okay, so now going to the next one. So actually now we come to a real theorem. So what corresponding to the Coulomb potential, what we were able to prove is that give really a rigorous upper bound in the sense that you can really extract not only the Hartree-Fock energy and this bosonic correlation energy, but also the exchange correlation, plus smaller order. And this is in some sense, you know, even Zavada did not do that. He basically added this thing by hand afterwards. But let's come back to that later. So, okay, so what was known before? So for regular potentials, a regular, for example, means that it's less singular than Coulomb for large K. It was already known before that you really get here equality. Equality means to leading order the Hartree-Fock energy, and to the next order the bosonic correlation energy. For regular potentials, this behaves proportional to Kf, so there is no log. So you need the Coulomb to get the log. So in a perturbative approach, where you take a potential, where you take a nice potential and a small parameter in front, and basically only retain the quadratic term, this one I showed you here, we basically analyzed that together with Marcello and the former student Felix Rexel from Tübingen. But the first non-perturbative approach, using this idea of Zavada, was given by Niels, Marcello, Benjamin and Robert, and Nam in two papers in 2018 and 2020. So in the first paper they proved an upper bound. That was a paper in CMP, and the second one where they really gave a lower bound, and they really proved that you can really in some sense sum up all these infinite diagrams, which was published in Invenciones. So what they used there is that the Fourier transform as a finite support, and that the potential should not be too large. But this too large was not because of summing up the diagrams, but for other reasons. And then a little bit later, with Martin and Nam, we basically got basically a different approach, which later on allowed us to really also do Coulomb. And this was actually funny because this was 2 years ago. So before this event, we put that on archive, and then the four guys here was under big pressure and were working hard in here to
put it on Tuesday, we put it on Wednesday. Because we agreed before to wait for you.
We were organizing the meeting.
Yeah, okay. Okay, but I wanted to relate it to this. And the condition and the potential was then given by that. So you see that the fall off here has to be faster than 1 over k to the fourth of vk. So actually, well, I will say a little bit. I just want to say the method we used with Martin was a little bit different, but still was different. But both of us used this bosonization method, which you introduced. I mean, which was really nice in the paper. But the method, as these guys did it, did not allow to basically extract the correlation energy. So, yeah. So now now I want to really basically describe the main idea. I'm pretty slow actually, yeah. So I want to describe the main idea. Maybe now I use the blackboard. So the idea which goes back to Sawada is actually taking the interaction, taking here this interaction and rewriting it so that you only retain the terms where you have a pair, one from outside and one from inside. So basically you can, this part here, when you move the A of P, so that satisfies the canonical anticommutation relation. If you anticommute the AP here over, you get something like B of K, A star P plus K. Now you move over the AP, then you have A star Q minus K and A of Q. And when moving this over, you have to move it through the Q minus K, so it gives you the P has to be equal to Q minus K. So you get something like minus, and then A star A of Q. So now you sum over, so basically here you sum over P, here you sum over Q, and here you also sum over Q. And this is really the number operator. And since we fixed the number of particles, I mean, you can say this is basically N. And what you get is V hat K. Now, this part here, this you sum over P, depending on K, you can denote that as the density rho of K minus N. So sum over K. So this rho K is basically, if you would do it in X space, this is the Fourier transform. This is basically the Fourier transform of that, if you want, formal way. And so as I said before, this is the sum over A star Q minus K, A of Q. So now what you can do is, you can distinguish all the cases. If Q minus K, you can start with Q minus K inside of the Fermi ball and Q outside of the Fermi ball. Then you can do plus, you can turn it round, you can say Q minus K outside of the Fermi ball and Q inside, and then the rest, the inside and outside. And that is something what we denote here as BK plus. The other one you can write as B minus K star, and the rest you can write, if you want, that this DK. Okay, and if you plug in here, you would get something like BK plus BK star plus DK star, and BK plus B minus K star plus DK. And now you multiply that out, and if you multiply this out, then you get, for example, of course B star B, BB, and B star B star. You also get BB star, you just commute them, then you get the 2, and the rest you can really actually extract and put into the Hartree-Fock energy. So you can extract also the Hartree-Fock energy by using the N, by using the commutator, which basically gives the volume of the loon, and also the D star K dk at K equals 0, which gives you the direct energy. Well, we have subtracted that anyway from the beginning, so that's not there. So in that sense, you get here the Hartree-Fock energy, and then of course, for the kinetic energy, you simply subtract the energy of the Fermi ball. So this is now the effective kinetic energy. What I told you before means that whenever you apply that to a pair of states, what you get is the difference corresponding to the Fermi ball. So that's what you have here. So this is always positive because we fix the number of, you have to think of, we perturb around the Fermi ball. So therefore, this is always positive. So now one has this. So in some sense, as you can see, what one could do, one could interpret these BKs as kind of a bosonic. And then the question is, so this is quadratic in these bosonic parts. If you now also could write the kinetic energy in kind of these terms of these these B's, then one only need to basically diagonalize this quadratic Hamiltonian and do so as if these were bosons. So this is not possible to write the kinetic energy like this. But what the 4 and 5 authors did was basically decomposing this case, looking at different patches, and on each patch you could do the kinetic energy. You can write it in this way. And then you can diagonalize that. This is not what we did. Namely, you can further, so each of these BK is a sum over these little BKs, and this little BKs is just a pair of two particles. And what one can do is to write the kinetic energy in these terms. Okay, so now the bosonization argument we used, and which in some sense also goes back to Sawada and some co-authors, is to now define as a fermionic pair, namely one from, so the P is outside and P minus K is inside. So if you want, you can describe, now I break the rule again. So the B star Kp, the B star is the so the A is the A star P, and A of P minus K. So basically what you do here, you create the hole inside and the particle outside. So this creates really a pair. Yeah, because you have to think of that the Fermi sea is filled, so you create the hole and you create the particle. And in some sense, so this satisfies this kind of the canonical commutation relation, but of course they are not really full bosons because of the fermion character. So if that would only the P and Q, this would be bosons, but you have something else. Now, in some sense, this is not small, but if you, for example, apply this on the filled Fermi sea, then you see it is zero, because the P minus K comes from inside, so if this is filled, then A star is zero, and if outside there is no particle, then this is also zero. So applied on the Fermi state, you really get that they are perfectly bosons. And in some sense, what we are using is that in average, this is smaller than the one. In particular, if you sum over all the looms. Then what is used so we will basically use that what we get from here is smaller than what you get from here. Okay, so now after basically doing this, then we can rewrite the kinetic energy in terms of the little b's, apart from errors coming from these b's with the d's and the d star d. This was not denoted, so that is basically the effective interaction. And now what is with the kinetic energy. So if you take the kinetic energy into the commutator with B or B star, what you get is basically this energy, this basically energy what you get when you put one particle out of the Fermi sea times B star. And if you think of, if the B's would satisfy the canonical commutation relation, then you would get the same commutator if the kinetic energy is just given by this B star B. And that, in some sense, allows us, apart from error terms, to replace the kinetic energy by something which is now also quadratic in the B's. Now the effective Hamiltonian here is now quadratic, and now the question is, can you diagonalize that, and do you get basically and do you get the right energy? So let me just wrap up. So basically, what you now do here for this upper bound, we just give a trial state. I mean, let me just. What I wanted to do. So you want to know what is. So now our trial state is. Of course, one has to choose one has to choose this state K here. But so what we want to do is to add Hn Ek of psi of S. So this is the same as the E psi of S E minus K Hn. And now what you get, so what was Hn? So first of all, it is the energy of Hartree-Fock. Then it is the effective Hamiltonian I told you. Then of course it is H, the kinetic energy minus, when you basically replace it by this B star Kp Pk. Yeah, and of course you get as an error term what you get from B star D plus D star D. So now what one has to do is to show that all these things are error terms. Yeah, and now one needs to choose the case so that E of k, that you can diagonalize, that you can, with this part, you can diagonalize this effective Hamiltonian. Now, you pretend you choose your k so as if they were purely bosons. So now the goal, if there are, if you choose the k so as if they're as if they were bosonic, then you get the energy of this correlation, of this bosonic correlation energy. Then you basically diagonalize the this part, so you get something which is diagonal in the B, so you get something E of k, P and Q, B star Kp, B star Kq, and plus something which comes from the exchange term, which comes from the fact that these things are not bosons, but really fermions. And the next goal is to show that this thing can be split in this, what is denoted as the correlation exchange energy plus error. And that's basically what is done. So now there is not enough time. If I would have enough time, I would have shown you that actually in this paper I mentioned, Martin came up with a really nice way to diagonalize it by choosing an ODE, where you get this out in a direct way. So this is if you want to know how you diagonalize that by an ODE, you have to look in the paper or in the PhD thesis of Martin, which is on the archive. Okay, so unfortunately for that I have no time. So now the next thing is you could ask, what is the spectrum of that? Sorry, this is a B star B. You can also look at the spectrum of this, and that's what you find in physics book. If you take Coulomb, and you ask what is the spectrum of what you get here, then you find that there is not only basically the normal spectrum you would expect, which is basically this lambda k and p, but there is one other thing which is called Plasmon mode, and which you get by an equation. But of course, for that you have to pretend to take. It's important basically to replace the mean field by Coulomb, and to take. If you take the thermodynamic limit, it's easier to calculate. Okay, but I don't want to say anything more about that since I'm done anyway. Okay.
Thank you for your talk. Are there any questions?
All clearness removed.
No questions?
So what's the range of the displacement that you need? So this K that parameterizes the moon. So does it need to be very small, or can you take it large enough in your clear state?
No, what
So
K?
when you the K that the displacement.
No, K goes to infinity. I mean here you displace it. Of course, for small k it behaves like that, and if the k is bigger than kf.
But do you need really small k's, or can you restrict to k large enough? I mean, for a lower bound, can you just decompose into boxes?
Well, k is bigger than 1, but you have to compare it with the kf, and you go with kf to infinity. So in that sense, you need to know how this behaves also for small k.
Okay.
Other questions? I have one. If you take something nastier than Coulomb, would you get different powers of the log?
Nastier than
Like more singular? Like in the formula for the energy?
Well, I mean, then you have to look at this diagram first. So I mean, for the box, I think it wouldn't make a big difference. But in a thermodynamic limit, you would get problems if you take something nasty.
So you cannot call anything more singular than Coulomb?
No, for the box, yes. It's not the problem. So what was the condition? What was allowed in the?
Anything that's L2.
Anything. Which can be pretty singular and for large k. I mean, pretty fast decay for. Well, since we're in a fixed box, you can.
So in any case, what you call Coulomb is the Fourier Coulomb, right? So it's 1 over k square.
Yeah. I think that's the usual way how you Coulomb on a torus.
I have one question. Maybe this is clear, but does this method apply to higher dimensions?
I mean, what is the physical meaning?
I'm sorry?
What is the physical meaning for higher dimensions? Aren't you happy with 3?
I mean, I'm just asking.
I thought you might ask for lower dimensions. But,
I mean, you can also ask for lower
you want to
dimensions.
wrap the
No, like,
dimensions
let's
also?
say d different than 3. Yeah, you can think about like a Gaussian flat surface.
No, I guess the method should work, but don't ask me what the result is.
Okay. Do you expect it to be better behaved for lower dimensions, or?
I really don't know. So,
And
next one.
other questions? No other questions? Then let's thank the speaker.